Hello everyone, I'm Cuauhtli from University of Primorska, and today I will present to you Dynamic Pinhole paper, our most recent work on developing interactive paper technology. Despite the digital age we live in, paper still plays an important role in our society. For example, we use it daily within our working environments, classrooms or at home. And this is true despite the fact this technology is 2000 years old. This lasting existence of paper is due to its unique properties such as the simplicity of use, endurance, and flexibility. Besides this, it is also very portable and does not require batteries to work. However, the digital mediums offer several advantages over paper. For instance, they can be easily updated, can play multimedia content, and with internet can give us access to almost infinite amount of information. This opens up an interesting question of how to seamlessly merge paper and digital content. Of course, we were not the first to think about this. It turns out there is an extensive body of literature on this topic. Note that we focus here only on visual augmentation of paper. So we organize prior work into the following matrix. It has two dimensions. Rows represent different interaction technologies, and columns represent the position of the light source. Doing this, we discover there are very few examples of systems where light source is placed beneath the paper. To the best of our knowledge, Illumi paper from Klamka and DokuDesk from Catherine are the only such examples. In our work, we place a touchscreen display beneath the paper in order to show and interact with digital content on the paper. Many people probably already tried this before us, but stopped as they observed this poor initial result. The problem of this naive approach is twofold. First, as we place a sheet of paper on top of a display, the paper sits at a slight offset from the in-focus image plane, and even though this distance is very small, it introduces substantial blur to the image. The second problem is related to the interaction of light with paper. Light needs to penetrate through paper in order to reach our eyes, and as this happens, light reflects, polarizes, and scatters. This again affects the image quality, in particular image brightness. To mitigate these problems, we decided to perforate the paper with tiny holes. This enables us to directly observe light from the display. The paper no longer acts as a light barrier on which the image is formed. Through this, we resolve the blur problem and brightness issue. However, perforation reduced the number of pixels we can observe. Part of the screen is occluded. For example, we cannot see pixels 6, 8, and 10. To reveal hidden pixels, we move the graphic. We rely on our brain, on our visual perception system, to correctly put this information together into a meaningful visual experience. And this is the end result. Normal paper. Image is badly affected by blur. Pinhole paper. Image is in focus but at low resolution. Dynamic pinhole paper. High resolution image. But now, please observe carefully. If I stop the video, the image quality immediately decreases. If I start again, you can again enjoy high resolution. As you can see, this video is not a trick. This concept just demonstrates how fantastic our brain is. It manages to generate a coherent visual experience out of a set of incomplete imagery. This concept opens up several interesting research questions, such as: can users perceive more quality detail in moving imagery? In other words, will our brains manage to combine this set of abstract images into a meaningful visual experience? If that's so, what is the optimal movement trajectory? Should we move in a circle? Should we move from left to right? For how much should we move? At what speed should we move? And finally, how will perforation affect existing paper functions such as writing and printing on paper? To answer these research questions, we fabricated pinhole paper. We perforated the standard 140 grams paper using a laser cutter. We made the smallest possible perforation of 0.25 millimeters. Note that the perforation pattern resembles a number 5 on a dice. As you will see later, this pattern is an important part of the concept. In order to run user studies, we designed a testing rig. You can see on the right. Users were seated down behind a desk on which we placed a tablet computer and a pinhole paper. Through the experiment, people were asked to keep their eyes at a constant distance to the display. To evaluate if users can perceive more detail in moving imagery, we conducted several user studies with 24 participants. We experimented with images and text. In our first study, observing images, participants were presented with an image for 2 seconds that was in one of the 3 possible movement modes, and then it moved to a different mode for 2 seconds. This routine was repeated 3 times per image. Afterwards, participants were asked to respond to questions. In which mode did you see more details? Which mode do you prefer? Independent variable was movement mode. We compared circular, linear, and static. The dependent variable were the question responses as cumulative votes. The results show that participants presumably saw more details when images were moving. When asked about their preferred movement, they chose linear mode. We did not detect any significant difference between static and circular. Again, to evaluate if users can perceive more detail in moving imagery, we conducted a user study on reading individual characters. In this study, participants were asked to read aloud a set of characters. The independent variables were movement mode, we compared circular, linear, and static modes. Typeface, we compared Arial and Times New Roman. Font size, we compared 8, 10, and 12 points. Letter case, we compared upper and lowercase letters. The dependent variables were error count and question responses. The results clearly show that fewer errors were committed in circular and linear modes. However, this effect decreases as the task became easier. No significant difference was detected between circular and linear mode. The results regarding other dependent variables are in our paper. Please refer to it. As in previous tasks, we asked participants to read aloud phrases and then to respond to one question. Which mode do you prefer? The independent variables were movement mode, we compared circular, linear, and static modes. Typeface, we compared Arial and Times New Roman. Font size, we compared 8, 10, and 12 points. The dependent variables were question responses. Results show that linear and circular were the most preferred modes. And again, as the complexity of the task increased, participants were more likely to prefer one of the movement modes, especially linear mode. For selecting minimum and optimal font size task, we asked participants to increase the font size until they could read aloud the phrase on the screen. After confirming the minimum font size, we asked participants to continue increasing the font size until they felt comfortable reading the text. The independent variables were movement mode, we compared circular, linear, and static modes. Typeface, we compared Arial and Times New Roman. The dependent variable was the font size. We can observe in results that participants were able to read at smaller font sizes in linear and circular modes, but no statistical difference was found. The same can be observed for optimal font size, but in this case, linear mode performed better than the other modes. In conclusion, all the experimentation continuously came to the same finding. First, users can perceive more detail in moving imagery, and second, users prefer linear over circular movement. But the key question still remains: what is the optimal velocity and movement amount? To answer this, we ran a study where participants were asked to read a phrase. We chose a small font size which made it impossible to read without movement. We asked participants to increase the speed of movement until they could read the phrase. After confirming their selection, they were instructed to increase the speed again, but this time until they considered it as optimal speed. The independent variables were movement trajectory. We compared circular 2.5 millimeters, circular 5 millimeters, circular 15 millimeters, and linear trajectory. The dependent variables were the minimal velocity and the optimal velocity. From results, we can observe consistent velocity across all movement trajectories, independently of the type and radius. For more results on this study, please check out the paper. Finally, in the last study, we first asked participants to select the minimum and comfortable size at which they could read the text printed on the perforated paper. The independent variables in this task were typeface. We compared Arial and Times New Roman. Font size, we compared 6, 8, 10, 12, and 14 points. The dependent variables were question responses as ratio. In this case, all participants were able to read at 8 points. However, the optimal size is shared between 10 and 12 points. Those are the sizes you commonly use in daily life. The last task of the last study consisted in signing and writing on a sheet of paper in two different areas, the unmodified paper and the pinhole paper. After signing or writing in both areas, participants responded 3 questions. Was it hard to sign your name? Did you feel uncomfortable signing your name? And are you satisfied with your signature? The independent variables were paper type, we compared normal and pinhole paper. Input type, we compared pen and pencil. The dependent variables were the question responses. And was it hard to sign your name? No statistical difference between the task and pen types were found, and participants did not find hard to perform the task. Regarding the difficulty of signing and writing, we can observe a statistical difference between the pen and the pencil, where pencil gave a more comfortable experience on signing and writing. Lastly, participants were satisfied with the way their signature looked on the pinhole surface. In conclusion, we have found evidence that moving digital content improves the perceived quality of imagery. Velocity is independent from the movement trajectory. Perforation does not affect writing and printing, and writing experience depends on the type of pen. So, why is this so important? Because this dynamic pinhole concept opens up several opportunities for affordable novel interactive paper applications. For example, geography exercises book that allows users to get digital augmented information on printed maps. It can be also used for math exercises to display short textual instructions, tutorials, and/or guidance. Another use case will be related to the translation of, for example, administrative forms. Perhaps more interesting is the fact that we believe this technique is not only limited to pinhole paper. We are now working on porting this idea to LED displays. Let me explain how. This is iPad Retina display under a microscope. As you can see, we are dealing with a grid of pixels aligned as close together as possible. We propose to change this pixel configuration. What happens if we remove 4 pixels from a 9 × 9 grid? Does this pattern remind you of something? Yes, you are right. It is the number 5 pattern we used in our perforation grid. If we succeeded to increase the resolution on pinhole paper grid, surely we should be able to achieve the same here. And if this is really true, we just found a way to drastically increase a display area with the same number of pixels. To be more precise, we made a 44% gain. Is this another Maxwell's demon paradox? We are working on answering this question, but I already have our first prototype with me. For more specific questions, collaboration, and information, do not hesitate and get in touch with us. Thank you.